Hi, welcome to the second video on my series of proof by induction. In this video, we're going to look at summations. So we're going to look at a sort of a basic example. We're going to look at the general algorithm for doing it. And in the next video, we're going to have a look at a more complicated example. So in this video, our goal is to prove that the sum of the natural numbers, i.e. 1 plus 2 plus 3 plus 4 up to n, is equal to n times n plus 1 over 2. Now, I've put an alternative proof here. So alternative, so you can write it out as Sn equal to 1 plus 2 plus 3 all the way up to n. You can then put this in reverse order, and you can match up each term. So compare 1 and n, 2 and n minus 1, 3 and n minus 2, all the way along. And you'll find out that when you add each of these terms together, you just get n plus 1. And well, there's n terms, so this is the same as n times n plus 1. And then what we've done is we've added Sn to itself, so we've got 2Sn. So all that's left is we need to divide both sides by 2, and we've found Sn. Now, quite a nice proof, very famous. You might have seen it before. You can find lots of videos out there online. But it's very sort of narrow. It only works for this particular example. Yes, there's a similar one for the geometric series. If you want to find the sum of a geometric series, you can do a very similar thing, except we multiply by r, and then we subtract from each other. However, it's very sort of specific case. It's a very specific case. It's not going to work for everything. So we want a method to be able to prove no matter what type of summation we're doing or dealing with. So let's have a look at sort of this algorithm. So first of all, as always, base case. Base case, pretty much always you're going to be considering when n equals 1. You've only got one thing in your sum, so that's going to be really easy. And then you're just putting 1 into the other side. Then we're going to assume it's true for n equals k. So we've got a sum of some function of m being the thing that changes. So up here, g of m was just m. So when m is 1, we get 1. When m is 2, we get 2. When m is 3, we get 3, and we're just adding each of them terms up until we get to n. G of m is just saying, well, it doesn't necessarily have to be m on its own. It could be m squared or log m or m squared plus 3m, m squared plus sine n, etc. And we're going to assume that the hypothesis that we've sort of started with is true. So it's equal to some function of k, or, well, some function of n, but in this case, n is k. And then we're going to consider n equals k plus 1. So we're going to consider the sum. We're then going to split the sum up like this. So we're going to write it as the sum up to the kth term, and then we're going to write the k plus 1 term separately. What this allows us to do is we can then take this assumption step up here and replace it. So this would become g of k plus 1 plus f of k. And usually at this point, the rest is just going to be a bit of algebraic manipulation, and we're going to be at our answer. I'm going to show you some tips as we go along with this example that are going to be useful for all the different other types of induction. So do still keep watching this video, even if this is a topic that you feel confident with. So let's have a look. So first of all, base case. Base case, n equals 1. So we're going to be doing the sum from m equals 1 to 1 of m. Well, that's just 1 plus, well, nothing, because 1's our only term. Putting 1 into the formula, we have 1 times 1 plus 1 over 2. And, well, this is in fact equal to 1. So true for base case. Next comes our assumption step. So we're going to assume it's true for n equal k, where k is an integer. Really important that we state this. K is not just some number, it has to be an integer. I.e., so we know what we're working with and what we've just assumed, the sum from m equals 1 to k of m is equal to k times k plus 1 over 2. So all we've done is replaced n with k in our original expression at the top here. Alright, next, Next is our consideration step. So we're going to consider instead the sum up to k plus 1. So m equals 1 to k plus 1 of m. I want to involve my assumptions, so we're going to replace k plus 1 with m, i.e. we're taking out the k plus 1 term, and the k plus 1 term is k plus 1. Leaving us with the sum up to k, and well, in our hypothesis, we saw that this was k times k plus 1 over 2. Now at this point, it becomes a bit of algebraic manipulation, but you're going to want to give yourself sort of a target. What are we aiming to produce? So we need a target. And to form your target, you're just going to want to put k plus 1 into our sort of hypothesis. So when we had that original expression at the top here involving n, we just want to replace n with k plus 1. So we have the sum of m equals 1 to k plus 1 of m is equal to k plus 1 times, well, it was k plus 1 plus 1, so k plus 2 over 2. So what we're trying to do is we're trying to craft this into this. That's our goal. And it could be useful to put our target because now we can start to craft it. A bit like a clay modeler would do. They see a picture, they will push in different areas. I've now got the picture that I'm after, and I've got my clay model, which is spinning around on this disk. If you want to sort of imagine that picture. Now, our target is only one fraction. In our example, we've got kind of a split up, not one fraction thing. We've also got that the top is factorized. So what I'm going to do is I'm going to combine these two fractions and I'm going to look for any factorizations, especially of either k plus 1 or k plus 2. So combining the two fractions, we get 2 times k plus 1 over 2 plus k times k plus 1 over 2. Now I see there's a factor of k plus 1 on top because this fraction has a factor of k plus 1 and this fraction has a factor of k plus 1. So k plus 1, this will be a 2 and this will be a k. And on the bottom we're going to have 2 because we have the same denominator, we can add these two fractions together. And well, this is exactly what our target was. So just by looking at the differences between what we have and our target and changing that, we've got closer to what we're after. We've realized there's a big difference. We have one fraction in our target, we have kind of multiple fractions in what we have. So by combining it together to make one fraction, hopefully we're going to get to something simpler, something that looks more like our target, which we have got. So I really recommend putting a target because it's going to make you very efficient. Now in the first video, we didn't actually see the final step. It's not really a step because it's every single time you do a question, you're going to put the same exact statement. It's never really going to change apart from one or two examples. It'll just be a number that will change. So to end off, we say, so as true for n equals k plus 1, when true for n equals k, and as true for base case. In this case, our base case was n equals 1. This is one of the things that could change. This number here as well could change. Potentially we'd be looking at, say, odd numbers, then it'd become a 2, etc. There's lots of sort of ways you could think about it, or all negative numbers, then it'd become a -1. But in this case, we're kind of doing a simple example. So we've got as true for base case n equals 1. It must be true for all n greater or equal to 1. Because what we've done is we've shown the dominoes fall. That's that first statement. We've then said they start falling from n equals 1, which kind of implies that it's true for all n greater or equal to 1. And finally, just need to state what we've used by mathematical induction. And that's it. that's all it is to it. I hope these tips are helpful. Summations is not the hardest type. I think you're going to find inequalities quite a tricky one, or potentially differentiation quite a tricky one. But we'll get to them when we see them. But the main idea here is we're trying to involve the assumption. When we do that consideration, once we've done that, our whole goal, our whole target is to involve the assumption. Once we involve the assumption, everything generally just falls out and we get to our answer. But thanks for watching. I've put some lecture notes in the description of the video. Feel free to have a look at them. They include some problems as well. What I want you to do, have a look at some of the problems and try them before you look at my solutions. It's the best way to learn, because you'll get stuck at one point and you'll see the solution and you'll realize, okay, what do I do when I get stuck next time? But yeah, thanks for watching, and in the next video we'll go through a more tricky example.